Hi everybody. I wanted to quickly talk to you a little bit about Newton's law of gravity, which I know you're going to be reading about, but I wanted to overview a few key points that are in the reading, and then when you look at the reading you can look a little bit more in depth. Alright, the first one is what we already know, that if we have two masses, let's say m1 and m2, separated by a distance r, and that's the center-to-center distance, and we'll say more about that later, the force between them is equal to big G, universal constant, times m1 times m2 over the distance between them squared. Now, this force here is equal and opposite on both masses. So m1 is pulled towards m2, m2 is pulled towards m1, and that force that one exerts on the other is the same. So it doesn't matter if one of the masses is like huge, like a big huge mass, and one of them is a smaller mass. It really doesn't matter. They will exert the same forces on one another. Sometimes you'll see this written a slightly different way, so that's point 2 that I want to make, which I think is worth making at this stage. I don't think your book gets into this that much, but I think it's a good way to think about it. Let's say one of the masses is m. It's, I'm just going to locate it over there. I have another mass, little m, just to emphasize the point that the relative sizes of the masses can be very different. And let's say the center of mass 1 to the center of mass 2 is a distance r. That force on little m, the one who I'm looking at, let's say I want to look at the force on little m, is always going to be directed towards the center of the object, no matter where it is. If it's over here, it's going to be directed that way. If it's over here, the force is that way. If it's over here, the force is that way. So there's another unit vector direction that's often used for radially symmetric situations, which is the r hat direction, which is the vector direction that points radially outward from an object that's symmetric spherically. And so the gravitational force of m on m would be equal to negative gmm over r squared r hat. That's the force on little m. The negative because it points towards the larger mass in the negative r hat direction. Similarly, if this were the force on big M, due to little m, it would actually point in the positive r hat direction in this coordinate system, but if I had my coordinate system centered on little m, it would point in the negative r hat direction. So it's just a good way. Sometimes you'll see this negative sign, and it just means it points radially inward. Okay, we'll usually use this form up here because it's a little more straightforward. Next thing is, let's take this same picture, let's analyze it a little bit more. Let's say that I have a mass, it's called big M, and I can be at a bunch of different places. Let's say I'm on the surface of the planet. So my distance, essentially, for all practical purposes, is just the radius of the planet. Oops, you can't see what I just drew. There we go. I have a planet, I have a mass on the planet, and the radius from the planet is essentially my distance from the center of the planet. So if I look at this, I could say, well, the force on me due to the planet is just gmm over r squared, where r is the radius of the planet. What's interesting is I have another name for that, mg, my weight. And so I can actually cancel out my mass and get a value for g on the surface of any object, not just the Earth. And it's equal to g times the mass of the planet divided by r squared, where this is going to be the radius of the planet. And so that's how we get g is 9.8. We plug in the mass of the Earth, radius of the Earth, we get 9.8. What's kind of cool is I can get in a little spaceship, fly to the moon. There I am, here's me on the moon. I can get g on the moon doing the same thing. It's just big G times the mass of the moon divided by the radius of the moon squared. And so this gives me the freedom to calculate the gravitational acceleration at any point. Now, I never really, this would all still be true, even if I wasn't actually on the planet's surface. So for example, I could be way out here in space, some distance that looks like it's approximately, above the Earth as big as the radius of the Earth, so 2 Earth radii away from the Earth. I could still talk about g, the value of g at that point. It would be just gm over r squared. And if I could have something on a surface, I could talk about how much it would weigh on that surface using that value of g. This value of g really becomes a measure of the strength of gravity near an object. Notice it didn't depend on the mass of the thing that was on it at any point that dropped out. That's why all objects fall at the same rate near the center of the Earth. That's why that happens. When Galileo dropped things off the Leaning Tower of Pisa, you know, big things and little things fell at the same rate because it cancels out here and our values of g are independent of the mass of the second object. And so even though we think of this little g as, you know, the acceleration due to gravity, like if we drop something, how quickly will it pick up speed, it has another name, which is called the gravitational field strength. Because it's really a measure of how strong gravity is due to the object that you're on or near. So sometimes you'll see this called acceleration due to gravity. Sometimes we'll actually call it the gravitational field strength. But it allows you to calculate how strong the gravity is when you're a certain distance r from a certain mass m. Okay, so there we go. I don't think you saw that because my picture might have been blocking it. Is that better? There's the moon. There's gravitational field strength. Okay, next thing, new paper. Let's continue to talk a little bit about what happens when you're near an object. One of the interesting things, and we've sort of been assuming it all along, and Isaac Newton just said this is true, it's a feature of his law, is that the entire mass of a sort of solid physical object acts as if it is concentrated at its center point, as if it's concentrated at the center of mass. So for a spherically symmetrical object, that's the center of the object, and all of that mass, if you just imagine it shrunk down to this infinite point, even if I'm like over here, this part of it doesn't really matter, you know, that I'm closer to, I'm really essentially closer to some of it and further than some of it, and all of those effects geometrically average out. And so for me, since I'm tiny, I'm already kind of a point mass, but even for something like the Earth, which isn't a point mass, it acts as if it's concentrated at its center, which is why we always use the center-to-center distance when we're calculating the gravitational force between two objects. Okay, now we know that this gravitational force, you know, is an inverse square law, so in general, that the force as a function of r is going to follow an inverse square, meaning it gets weaker and weaker as you get further away. So if I'm way out here, the radius is bigger, the force of gravity is less. If I'm on the surface, the force of gravity is more, and I actually call that my weight when I'm on the surface because it's like your physical weight. Here's a question. What if I'm inside the Earth? What's the force of gravity on the Earth, of gravity on me at that point? Well, it turns out Isaac Newton explained that as well. Imagine at your distance, if you're burrowed within a solid object, that you could sort of enclose the mass that falls within the radius from, you know, measured from the center where you're standing. So you can look at just this here. Look at all that. That's called the mass enclosed. It turns out the force of gravity on you at that point doesn't depend on any of this stuff outside. It only depends on the enclosed mass. And you're going to have some problems that ask you to work on that. And that's a really cool feature of the law of gravity. It's also going to be true of electricity, we're going to see in our next unit. So if I'm standing here, let's say I burrowed down into the Earth, I went like down, 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 and I got down to here, and I was at the edge of the core of the Earth. So the mantle and the crust and all that business was behind me. The only mass that would actually affect and pull on me with gravity is the mass of the core. So it would amount to just figuring out the mass of what's in that enclosed radius, and then once I know that, I could calculate the force of gravity. It's just going to be g times mass enclosed times my mass over the radius squared. And some cool things happen when you do the math here. We're not going to do it in this video, we'll do it on Monday. Some really cool stuff happens when you start to apply this law. Okay. The other side effect of that is, let's say I had a shell of gravity. Let's say I had a weird shell planet, that it was just like a little shell of mass like that. All the mass of the planet was concentrated in this thin shell, and I'm like somewhere out here at a distance r. there's me. So if I'm out here, it turns out that it would basically behave like this. All this mass would act as if it were concentrated down at the center, at the dot, shrunk it down, so there it is, and there's me at my mass m, and basically the force would just be gmm over r squared, where r is this distance from the center to there. So that's cool. What if I'm over here, inside the shell, like beyond it? So if you look over here, is there any enclosed mass? No. So there's no mass enclosed in that sphere, in that spherical shell. So if this is point A, the force at A would just be like if all of this were shrunken down to a dot. But if I were at point B inside the shell, you know, where there was no mass, the force at B is 0. And that's cool too. So we'll talk about all of this a little bit, but you'll read about it. There's a couple of problems that see if you've gotten this concept, conceptual and otherwise. But I hope this gives you a little bit of an overview of the main ideas in the reading. All right, thanks guys. Bye.